In Chapter 8, we're going to discuss fundamental theorem of calculus. The name sounds important because it is important, as it's going to allow us to efficiently calculate areas on the curves. Let's recall what a definite integral is, and that is the area under the graph of the function, between the graph of the function and the x-axis, between the two given endpoints. This definition alone will motivate all of these properties of the definite integral. For example, if I take the integral from a to a, let's sketch this out. So what I have is some function f of x. Let's make it above the x-axis, just for general case consideration. And if I have a point A, I'm going to calculate the area under the graph above the x-axis from A to A. So the area of this line here. Well, of course, this area is equal to 0, which is why any integral from the point to itself is also equal to 0. The next integral says that if I am interested in the area between the graph of a function, between the points A and C, I can break it up to be areas between two other points. And again, let's justify this with a simple graph. So if this again is my function, and I have points A and C, if I'm interested in computing the area between A and C, as the first integral here states, what I can do instead is find some point B in between, let's say here. Doesn't have to be exactly in the middle, so let me make it clear that it shouldn't have to be anywhere in particular. And then, instead of computing the whole area, I can first compute the area between A and B, which is this integral, and then compute the area between A and C, B and C, which is this integral. The next integral simply says that if you have a constant, you can factor it outside of the integral if this constant does not depend on x. That just means that if my function is actually somehow vertically stretched out, I can calculate the original area and then multiply it by the scalar factor. These three properties can actually be motivated by the fact that the integral itself is just a summation. Remember that it's a summation of the areas of the rectangles. And this corresponds directly to the properties of summations that say that if the sum has a constant times whatever the sum is taken over, then I can factor this constant out. Same thing here. If I have a summation or an integral of the sum or difference of two different functions, then I can simply split them up and calculate each integral separately. So let's make sure we also include a negative in here for a possibility of that. In this last one, I'm not going to go into the minute nuances of explaining where this minus comes from. The idea is that if you want to switch the order of the left and the right endpoints of the integral, then you can do so by introducing an extra minus in the front. Now we can use these properties immediately to help us with the calculations of the areas and justifying some of the more efficient calculations. So far, all we know is that a definite integral is the area between the graph of the function and the x-axis. So all we have to do, or all we can do, is draw graphs. So here, what I have is the graph is y equals x, which means that it's a diagonal line like this, and I'm interested in computing the area between -1 and 1. So let's say -1 here and 1 over here. This is now the area I am interested in. This example is here to remind us that an integral is always a signed area. If the area falls below the x-axis, it counts negatively. If it falls above the x-axis, it counts positively. So what we notice here is that both of those areas are exactly the same, which means that the negative will fully cancel out the positive and the integral will be equal to 0. For this next integral here, we've already seen some that are like that. I can draw the line x plus 3 and then calculate the integral that way, or using one of the properties on the previous slide, I can split this integral into two. I can calculate the area under y equals x between the 2 points 0 and 2, and then add the area between the graph of 3 and the x-axis. For each one of these, then I will have to create a separate little graph But splitting them up like this sometimes yields much easier graphs to figure out and to calculate. So y equals x here. There we go. That's my graph y equals x. And I'm interested in the area between 0 and 2. So this area right here. Now this is just a triangle of base 2 and height 2. So overall, this is going to be half of base times height plus whatever this integral yields. Now the graph y equals 3 is simply a horizontal line at 3. And again, I'm interested in the area between 0 and 2. So I'm interested in this area. This is a rectangle, so this is an even easier one to figure out. It's 2 by 3 rectangle, so altogether I'm going to have a 6, and if I add both of these numbers up, I'm going to get an 8. So far, nothing new, just reviewing what we've done before. This example is here to also justify the fact that sometimes, even once we develop more efficient ways to calculate more complex integrals, sometimes it's worth going back to the basics and the understanding of the definite integral as the area, because this will truly simplify some calculations. So I know we haven't worked much with trigonometric functions yet, but this will not require a lot of reminding. All I need to do is sketch a graph of y equals sine x, which is a sinusoidal curve like this, and I know I have to go between 0 and 2 pi, so one full period. This is pi, and this is 2 pi. Now, again, the integral is the area between the graph and the x-axis, so I am now calculating the area covered by this region and the area covered by this region. Be mindful, once again, that the integral is a signed area, which means that if it falls below the x-axis, it's going to count negatively, and if it falls above, it's going to count positively. Sine is a fully symmetric function here, so both of these areas are going to be the same. Be careful, they're not actually semicircles. They are a sinusoidal curve, which is a very different shape, but they will cancel each other out, so just like in the first example, I am in fact going to get a 0. Now notice that here I've actually gotten very lucky, because if the integral asked me to calculate between 0 and any other point, let's say over here, I wouldn't have had the area that is positive and the area that is negative cancel out entirely. I would have had to calculate the area of this awkward little, really non-standard looking piece that I have no idea how to do. And this leads us to really think about the integral and the area as a function itself. As I move from 0, from the left-hand point here, forward, I am covering some amount of area, and anywhere I'm told to stop, dictated by the integral, I have to calculate the area covered up until that point. But if I continue forward, the area, and therefore the actual value of the integral, is going to change. Let's take a look at this interactively. So what I have here is a cubic function that I've introduced. I've also used the built-in Desmos calculator for integrals to calculate the integral between, that is the area of the curve between the function and the x-axis, between the points a and b. So notice that this number appearing in the box here will actually calculate actively the integral when I fix the left and the right endpoints here. Now I'm going to keep the a, so the left-hand point, fixed at 0, and I'm going to change the value of the point b. So I'm going to vary my integral according to the right endpoint. So first, let's take a look at the graph. So keep your eyes on the graph. As I start here, and I move my point to the right, the integral itself is going to increase. And that is, of course, because the area being covered increases. In fact, it's going to increase up until this point here. And then after that, I'm going to start acquiring negative area, and the integral value should start decreasing because of that. Let's see if that's actually what happens to the integral. So now pay attention to this number in the box on the left-hand side to see if it follows the rules, or rather the logic that we just discovered. So this number should be increasing all the way through. It's keeping track, very careful of like all the decimal places. So see, we're increasing up until this point, and then after this point, the integral starts getting smaller and smaller and smaller up until here. After this point, I'm again going to be acquiring positive area, so now my integral value is increasing again. What we're going to try to do is think about how this process is actually a function of the right endpoint b here. If I change the position of the right end of the interval, then I change the value of the integral itself. And I can model that in terms of a function. What we're going to think about is what happens when I make a very small change. So instead of moving the right endpoint from one point to a faraway point, I'm going to think about what happens if I move it just a little bit. How is that newly added little bit can be calculated separately. What we have is a function, f of x. I'm going to keep it general, not just to the cubic. That was in my Desmos demonstration. I'm going to fix the left endpoint a, and I'm going to keep this right endpoint x varied. So this guy is fixed, whereas the right endpoint is going to change or vary. What I would like to do is think about as x moves to the right, how does the area that is covered, or the integral, actually change value? Now, because I'm going to keep track of the area, I'm going to give it a name. Let's call this a of x, because it depends on x, it depends on the position of x, so this value for the area actually is a function of x. What I would then like to do is think about what happens if I move this point to the right just a little bit. So I introduce a very small change here. Now I'm going to draw it not as a very small change because I don't want to create microscopic drawings, but this is supposed to be a very, very small number, a very thin sliver. So here I'm going to have x plus h, so this distance here is h, and this is going to be something that is really quite small. So what happened here? How can I now describe the newly covered area that includes my old area and includes my new sliver? So first of all, because the area is a function of the right endpoint, the area now covered from a to x plus h is actually a of x plus h, right? This entire area can now be the function of the right endpoint the way that we defined it here. Now, this new area is actually my old area from a to x, plus this newly added little skinny sliver. Now, if it's really actually very, very thin, then by the same logic as we kind of used for Riemann sums, I can say that it's well approximated by a rectangle. If the width here tends towards 0, then the shape of this object is going to approach a rectangle. Now, rectangles' areas are easy to count. We just need the width, which in this case is h, and we need the height, which in this case can be approximated, or rather evaluated in terms of our function. The height here, much like in the Riemann sums calculations, is going to be f of x. I plug my value into the function in order to figure out the vertical distance. So my new area is my old area plus a rectangle. So I have, let me actually write this down. So this is new area, this is my old area, and then I need to add an area of my rectangle, which is f of x times h, which is just width times height. So area of a thin rectangular sliver. Now I have this expression here, and what I would like to think about is what does that look like? Does that look familiar? Can I somehow change this up, or can I somehow maybe solve it for something? What I'm going to originally solve it for is this f of x. It's the function that I know. It's the function that I've been given. So if I create another expression for f of x, maybe that's going to tell me something about the overall situation. So if I solve this entire equation for f of x, what I'm going to get is I'm going to have to move this guy over to the left. So I'm going to get a of x plus h minus a of x, and then I'm going to divide by this h. divided by h. Does that look like a familiar expression, or rather just the right-hand side? Does that seem like something we have seen before, maybe in Calculus 1? Maybe you're still having nightmares about this expression that you would have seen that was called the difference quotient, and now everything is coming back. This looks like the definition of the derivative. The only difference is in the definition of the derivative, you also had a limit in the front. And this, of course, also makes sense to do here, because what we actually are trying to do is make this h as little as possible, and therefore actually make this area approach a rectangle. This approximation of the function gets better and better if we introduce the limit as h goes to 0. Now, once we do that, of course, what we end up with is exactly the definition of the derivative. So on the one hand, this is equal to f of x, and on the other hand, this is equal to the derivative of the actual area function. So what I have, eliminating the middle, is f of x is actually equal to the derivative of the area. My function and the area between the function and the x-axis are connected by this really deep and meaningful relation. This is what lies at the crux of the fundamental theorem of calculus, part 1. Before we get to the actual fundamental theorem of calculus statement, let's introduce a definition we're going to use throughout: an antiderivative. And that's exactly what we have just seen. Given a function f of x, so in our case, we were given a graph of f of x, a function a of x is called the antiderivative if its derivative is the given function. So what we're normally used to doing is that given a function, I take a derivative of it, and then I think about that as my next function. Here, it's kind of like going backwards. So let's think about the chain of differentiation as we would have it built. If I start with the function f of x and I take a derivative, so I differentiate here, what I create is f prime of x, or df by dx if you prefer Leibniz notation. If I take another derivative, so if I differentiate again, I will have a second derivative of the function, and so on, as long as the function is infinitely differentiable. What happens if I go and think about where did my original function come from? What if this is itself a derivative of something? What is that something going to be? And the answer is antiderivative. So if I step one step back here and think about that, the name of the function here is the antiderivative. Now the name is pretty descriptive, right? So this also means that if I start with the function's derivative, one step back is it's going to be its own derivative. Thinking of antiderivatives is always thinking of the given function as someone else's derivative. Whose derivative did we have to take in order to end up with the function at hand? The fundamental theorem of calculus now says exactly what we've seen, is that if I have a definite integral, the area under the curve between the two given points, then that area is actually the antiderivative of my original function. To me, this has always been a very profound and somewhat surprising result. The fact that the area under the curve is connected to the derivative of the function. Now, the reason this result is so useful is that it gives us a way to compute the definite integral, not just as an area, but rather as an antiderivative. We already know how to take derivatives of functions. For antiderivatives, we simply have to reverse the process. So we can come up with an algebraic way to compute areas under curves that are definite integrals. This also gives the direct geometric or graphical relationship between the area under the curve, of course, and the function itself. So for a really quick recap of how derivatives and antiderivatives are connected to the graph of the function, let's say I have a graph of some function f of x. If I take a derivative at some point, the derivative is the slope of the tangent line, and if I compute the definite integral between some point A and some point X over here, then the area bounded by the function and the x-axis is the antiderivative. This is somehow connected to the derivative, and this is connected to the antiderivative. Now, I am generally not great with articles, but I do mean an antiderivative in this case, and that is because it's not going to be the only one. So this is something that we're going to have to think about a little bit as we start computing some general antiderivatives. In this table, and you might have seen something similar in Calculus 1, where you first developed understanding of antiderivatives, all we're thinking about is really just reversing the process. So the first column is the original function, and the second column is the derivative. We're going to try to go backwards using our understanding of how to go forwards. So if I have a 3, what did I have to take a derivative of to produce a 3? Well, this one is fairly straightforward. If my variable is x, I have to take a derivative of 3x. Now, if I have x squared as a function, what is its derivative? Well, this is just 2x, and this is just to remind ourselves about how the power rule works. The power comes down, and you reduce it by 1. So if I end up with x as the derivative, what did I have to start with? Well, if I ended up with 2x here, I probably had to start with x squared, but then, of course, the derivative of that would have been 2x, so I would have ended up with an extra 2, and I have to compensate for that. Compensating for constants, it's fairly straightforward. You just introduce a factor of that constant in front. Now, the nice thing about antiderivation is that you can always check it using differentiation. So if this is what you think the original function is, take a derivative of it now. Derivative taking is an easier process. Will you get what you want? So if I take a derivative of that, remember the constant multiple rule, we leave the constant alone. We bring the power down and reduce it by 1. 1/2 times 2 will cancel out, and we will get our x back. I will leave most of the table for you to fill out to really practice these small steps of thinking about the reverse process that are going to be essential in getting comfortable with antiderivatives. So please do not just skip this. Fill this out. Really think about what you're getting and where. And I will then concentrate on some general observations about the derivatives as well as some useful derivatives. So as we noticed in the table, if I would like to find an antiderivative of 2x, for example, then it can be x squared. Antiderivative, once again, means that if I take a derivative of it, I'll end up with my original function. Now, the thing though is x squared is an antiderivative, but so is x squared plus 3. Because if I take the derivative of that, I will get 2x anyway. Remember that the derivative of a constant is just 0. So in fact, any constant that I choose to add or subtract will not affect my antiderivative at all. That is why we say that an antiderivative is an antiderivative, not the antiderivative. In general, an antiderivative of 2x can be any of these, and the most general format will be x squared plus c, where c is any arbitrary constant. Antiderivative, therefore, is not unique and is always defined up to this constant c. What this also gives rise to is the following fact. If I have two different antiderivatives of the exact same function, then they have to differ in only a constant. They cannot be two different functions at their sort of root in nature. The only difference between two different antiderivatives of the exact same function can be just a number. So the next thing that we're going to introduce is the so-called indefinite integral. Notice the only difference is I don't actually have the interval as a part of my definition here, and that is because the indefinite integral will not refer to any specific area, but rather will describe a general antiderivative of f of x. Since there are no boundaries, no specific area is given, that antiderivative, and therefore this indefinite integral, can only be found up to this constant c. Now this means that up to a constant, we would still really like to know some common general antiderivatives of the functions that we deal with all the time. So let's think about what might those be. For example, if I have an antiderivative of a constant k, I am taking it with respect to x, meaning x is my variable, then I know that the only way I would have ended up with k as the derivative of something would be to have taken a derivative of kx to begin with. Right? Again, you can always check the antiderivative by differentiation. If I take a derivative of the right-hand side, will I end up with what's inside my integral? And in this case, yes. Now remember, antiderivatives are only defined up to a constant, so I will have to also introduce this plus c here. Now the plus doesn't mean that it's always positive. C in itself could be negative, like it could be -2, but we keep the plus just as a general notation. What about if I have x to some power n dx? So if I ended up with x to power n as a derivative of something, what did that something have to be? Well, I know that when I differentiate, the power comes down and the power gets reduced by 1. That means that I had to start with a power 1 more. But then in my differentiation process, the power would have also come down in the front as a number, but it doesn't appear to be here, which means that I have to compensate for that in order to not have that happen. So here I will have x to power n plus 1 divided by n plus 1 plus a constant. Again, notice that I can take the derivative of this right-hand side to double make sure that I actually have the correct result back. Okay? What about, for example, the derivative of negative powers? Will this still work out? Will this always hold no matter what? What are some values of n here that will not work? Well, I notice that here n cannot be equal to -1. So in fact, this formula has one caveat. N cannot be -1. Other than that, this power rule is quite powerful. It's going to work for every other power. Negative, fractional, which means roots, anything like that will work except for -1. Well, let's see what happens with -1. So if my n is -1 here, what I actually have is 1 over x, whose derivative is 1 over x. What did I have to take a derivative of to produce 1 over x? It is a bit of an unexpected function. It's not a power function. And if you remember your differentiation rules well, you will remember that it's actually ln of x, natural logarithm of x, plus a constant. This leads us to think about, what about antiderivatives of logarithms and exponential functions? Antiderivative of logarithm itself is actually quite difficult to find, and we will get to that at some point in the course, but the antiderivatives of exponential functions are really easy. Remember that exponential functions, being egoistic, had derivatives of themselves equal to themselves. So antiderivatives of them are also just themselves. This gets a little more complicated if we start introducing constants into the power as a factor of the power, and we'll have to compensate for that, keeping the chain rule in mind. So here, again, I encourage you to actually really think through this, but here I'm going to get e to the power of kx. The power doesn't change, but I'm going to divide by k to compensate for what the chain rule would have produced. Some of the other things that are useful to know, and we will come across later in the course as well, are, for example, derivatives of trigonometric functions or antiderivatives of trigonometric functions. So sine x and cosine x being the main two, and then I'll leave the tangent and secant and whatnot for later. What did I have to take a derivative of to produce sine of x? Well, I had to take a derivative of cosine, but then it would have given me minus sine, which means I have to include the negative to make sure that this all actually works out. Same for cosine. The antiderivative of cosine is sine of x. With all of these in mind, we can already do quite a bit of computations with antiderivatives. So these are just a few examples that we're going to consider. Let's take a look at the first one. I'm going to do these in a lot of detail, and the more practice you get, the more steps you can skip or not fully write out. But for the first few, I'm going to be quite careful about going through every single step. So the first thing here is, instead of taking the antiderivative of this entire polynomial, I am going to apply the property of integral that says that I can split this up across the pluses and minuses. So this is the same as the integral of 3x squared dx plus the integral of 4x dx plus the integral of 5 dx. Once I have that, the next thing I can also do, I notice, is to take out the constants. So 3 and 4 and 5 can go in front of their corresponding integral signs. So because I'm a little short on space here, I'm actually just going to move them outside like this. Once I'm at this step, I notice that all the integrals that I have left are those that I can compute the antiderivatives for exactly. The antiderivative of x squared is the antiderivative that the power rule would apply to. X squared for n here. Notice that the general rule, if said verbally, means that I add 1 to the power and I divide by the new power. So I'm going to add 1 to the power, keeping in mind that there is also this 3 in the front that I have to carry over. So for the antiderivative, I add 1 to the power and I divide by that same number. Plus 4. Now this is also a power rule, and the power here is 1. I add 1 to that number, so it's 2, and divide by that same power. Plus, and what do we have here? Well, there seemingly is nothing there, but really there's a 1 there. And the 1 can be thought of as x to power 0. So I can also apply the power rule here, although it's a bit of an overkill. I also can realize that in order for me to get 1 as a derivative of something, that something just had to be x itself. So this will give me 5x. And all together, I have to remember that all of these were indefinite integrals, so each one of them came with a constant. I can combine them all to have that one constant at the end. Let's take a look at this next one here. So one thing I can do right away is take out the 3, and I will have 1 over x squared dx. Now I notice that I didn't have any rules that will allow me to calculate the antiderivative of a quotient. So that's not something that I can apply, and therefore I can think about what can I do to massage this function. Well, 1 over x squared is actually simply x to the negative 2, right? When the power appears on the bottom, it's simply a negative power. Now this means that I can apply the power rule to it. It's going to be applied in the exact same way, except you just got to be a little bit more careful with the negative numbers. The rule is the same. We add 1 to this number and we divide by that number. So I'll rewrite my constant of 3 in the beginning, and then I have x minus 2 plus 1 minus 2 plus 1. Overall plus a constant. So you can of course simplify this expression. I'll leave this last step up to you, but do be very careful with adding ones to negative numbers. Somehow it just works in the ways that sometimes it's just worth spending the time to write the extra line down than do it in your head. For this next one here, what we have is x times x plus 1. Now notice that while there is a rule that allows me to break up integrals over plus and minus signs if they're minuses, there is no rule that allows me to break this over a product. So this is not the same as computing the antiderivative of x times the antiderivative of x plus 1. Just like the product rule for differentiation, products need to be treated way more carefully. So don't make this mistake of trying to break it up this way. In order for me to even do anything with this integral, the only thing I can do right away is factor it out. So I'm going to have x squared plus x dx. Once I have it down to this form, I can in fact split everything across the plus like I've done before and compute these two integrals separately. So I'll leave this to you. Same thing for this. There's no rule that we've discovered so far that will allow us to take integral of a quotient. So by no means is this the integral of x squared plus 2 divided by the integral of x. This is just wrong. Don't do it. So we cannot do that, meaning we have to somehow change up the function into something that we can actually take an antiderivative of. One thing we can do is sort of undo the common denominators here. Split across the denominator. So I'm going to have x squared over x plus 1 over x dx. And I can simplify this a little bit more. What do I have? X plus 1 over x dx. And now these two integrals, I can again do one at a time. The integral of x is going to be x squared over 2. The integral of 1 over x is one of those interesting ones, ln of x. And don't forget your constant. I'm going to leave the last two for you to play around with in terms of where the constants actually occur. What I encourage you to do is when you come up with an answer, to check it using differentiation. So once you have your answer, take a derivative of that and make sure that what you get is the actual number inside the integral, not something else. That way you can be certain that you've placed all of your constants into the right spots.